All right, so next video we are on slide 16 of chapter 4. We are making solutions and dealing with molarity concentrations. So when I look at this problem, I'm going to take a solid compound. It's called copper sulfate pentahydrate. Okay, the bottle's right here. It's actually copper 2 because copper can show different charge states. But so I have a bottle of this solid. I'm going to weigh out 10 grams of the compound. I'm going to dissolve it in a flask with 100 mils of water, and then I'm going to add more water until I get to a total volume of 250 milliliters. Okay? When I do that and I finish, I want to know what's the concentration of the solution that I just made. So, what do we need to do? Well, essentially, we know the molarity equals the moles over the liters. So I'm going to treat this one molarity equals the moles of the compound copper 2 sulfate, over the liters of solution that I'm making. Now, talk a little bit about the compound, because the compound itself may have some information that throws you off. Again, sometimes in lab we deal with these compounds, so you may have seen this before. But copper 2 sulfate pentahydrate, the word pentahydrate stands for 5 waters. Pentas 5, hydrate means water. Okay? So if it's copper 2 sulfate pentahydrate, the compound in that bottle is actually CuSO4 with 5 H2O molecules. Okay? Now, what does that mean? Well, essentially, a lot of ionic compounds have a property where the crystals will absorb water from the air. That is called a hygroscopic compound. If you go to the beach, the salt shakers on the table at the beach, because the beach is always very humid, the salt shakers, if you don't do anything to stop it, they'll absorb moisture from the air, and all the salt will solidify into one big chunk that you can't shake out of the shaker anymore. So to prevent that from happening, they add rice to the salt, because the rice will absorb the water quicker than the salt will, and that'll keep the salt from clumping up so much. Okay, so many ionic compounds are hygroscopic. Well, a chemical company that sells this bottle, if they tell you that it's pure copper sulfate, they would be lying. Because when they make this compound, now you can spend more money and get one that's called copper 2 sulfate anhydrous, which means there's no water in there. It's harder for them to make that. It's more expensive. So most of the time in labs, if you're not worried about, if you just factor in the calculations, the fact there's some water in there, then you buy the cheap stuff and you just work with it. Okay? So this compound, the crystal structure, there are water molecules all stuck in the crystals, and on average, the chemical company is telling me that there are 5 water molecules stuck on each copper sulfate formula unit. All right? Well, that means that if I'm going to weigh this compound out, the water is going to be part of the weight. All right? So they told me in the beginning of this problem, I'm going to weigh out 10 grams of the compound. So it's 10 grams of copper 2 sulfate pentahydrate. Now, I need to get the moles of the compound, so I'm going to divide the 10 grams by the molecular weight. And again, if you want to be good at chemistry, there are certain basic calculations you need to learn. So I should do 10 grams times 1 mole over the molecular weight, and I'm going to end up doing the 10 divided by the molecular weight when I do my calculation. You need to memorize that. We do it so often in this class that I don't want you to have to think your way through and set it up and cancel units out every time. You should be getting, by this point, you should be at the point where you know to go from grams to moles, you always divide by the molecular weight. Okay, so if you add up the molecular weight of this compound, I just happen to remember that it's 249.6. So I'm going to do 10 grams divided by 249.6. That's the molecular weight of this compound. If I do that, I get 0.04006. moles of the CuSO4. Now, once I weigh that out and I dissolve it into the water, these 5 water molecules are just going to become part of the solvent. They're going to like break free and just become part of the liquid, and I don't have to worry about them anymore. The only part of the problem where they matter is when I'm weighing the compound out in the first place. When I get out of this bottle, it has water in the structure. I have to account for that weight. So that's what I did here to get to the moles. And then once I dissolve it, the waters disappear. Okay, so that's the moles of the compound. That's what's going to go on top of my equation. 0.04006 moles of CuSO4. That's the moles that I weighed out. Then I look at the problem and said they added 100 mils of water to get the stuff to dissolve. But that's, remember in the example I gave a minute ago, that was the add half the water, shake it up till it's dissolved. But then they filled it up to 250. So the final volume of the solution is 250 milliliters, which if I divide by 1,000, that's 0.25 liters. So that's what I'm going to put here, 0.25 liters. And now my molarity is going to be the moles divided by the liters. If I just do that on my calculator, that's going to equal my answer. And I got 0.160256. Technically, this problem should only have 1 sig fig. Usually, in a case like that, is probably when I made this problem, I wasn't paying attention to sig figs. So whatever you want to write, it should be around 0.16 molar. If you want to round that to 0.2 because it makes you feel better, go for it. All right, we're going to move on to our next problem. So this slide has 5 problems on it. We're not going to work all 5, maybe work 2 or 3 of them, and you can work the rest of them on your own. But what you'll notice on these problems is that you need to add up, every time you do one of these, you have to add up the molecular weight. Again, I've told you guys a few times when you're adding up molecular weights, it's important to just round off most of the elements to a whole number if they're really close to a whole number. If it's not close to a whole number, keep 1 decimal place. As you work these problems, you'll realize that the more extra work you do, it's going to take you a lot longer to do these problems than it should, and we have to be efficient. We got to move through these problems because on the test, you're going to have a lot of problems to do. You got to be ready for that, okay? So first question, if I have 4 grams of sodium hydroxide and I make 0.5 liters of solution, what's the molarity? So this one's pretty easy. Again, the molarity equals the moles over the liters. They gave me the grams of sodium hydroxide, so I can convert that into moles. They gave me the volume. If I do the moles divided by the volume, I get the molarity. Okay, so I'm just going to talk through this one. The molecular weight of sodium hydroxide is 23 plus 16 plus 1 is 40. So I would do 4 grams divided by 40. That would give me 0.1 moles. So my top is going to be 0.1 moles. Okay, the problem directly tells me I'm making 0.5 liters, so the bottom is going to be 0.5 liters. So then my molarity, I just divide those 2 numbers. The molarity is going to be 0.2 molar NaOH. And it's important to write your answer in the right form. You do want the right number of sig figs. So technically, I should have actually written 0.20 molar sodium hydroxide because I want 2 sig figs. Okay, but I put the number, I put the unit as the capital M, and then really I like it if you specify the actual compound because it's the molarity of the sodium hydroxide that we made. Okay, next problem. The next problem is very similar. I'm just going to skip over that one because I don't want to work 2 that are the same. So we're going to go to number 3. Number 3 is the same. So we're going to go to number 4. Okay, so stomach acid is 0.1 molar hydrochloric acid solution. How many moles of HCl are present if I have 1,500 milliliters? All right. So I'm working for my, so there's 2 ways to work this problem. I'll work it both ways. First, I could do molarity equals moles over liters. I could just treat that as an algebraic equation. I can plug in the molarity as 0.1. The volume is 1,500 milliliters. Divide by 1,000, that's 1.5 liters. And then I can make the moles as the unknown. That could be my x term. So I have 0.1 equals x over 1.5. So that means if I solve for x equals 0.15 moles of HCl. And that's it. So that's one way to solve this problem. The other way would be more dimensional analysis approach, where if I start out with the 1,500 milliliters of solution and they ask me how many moles of HCl there are. So in this case, I'm going to use the molarity as a conversion unit. So if I have molarity is moles per liter, that means I need to have my volume in liters. So again, I got to get my 1,000 milliliters to 1 liter. So I'm going to divide by 1,000 right there. And then my molarity they gave me was 0.1 molar. So I know that's going to be 0.1 moles to 1 liter. That's my molarity term right there. And then if I work that out, I should get the same answer, 0.15. So I just worked the problem with two very different approaches. I, as a student, always like to use the equation and do the algebraic solving for x. But if you're used to the dimensional analysis approach, that's fine too. I'll take either way, just get to the answer. All right, and then the last question. So calculate the grams of KCl that must be dissolved to make 0.25 liters of a 2 molar solution. So this would be a very common problem. If you are making a solution, the first calculation you have to do if you're going to make a solution is you have to decide how much of the solute do you need. Because you have to get your glassware, and again, if I'm making a 0.25 liters of solution, that's 250 milliliters. So I'm going to get a 250 milliliter volumetric flask. But I have to put the right amount of solid in there to fill it up with water to give me the concentration I want. Okay, so this is a good problem to do that work. So again, if I set it up, the molarity equals the moles over the liters. They told me I want to make 0.25 liters. They told me that I want to make 2.0 molar. And I need to figure out how much KCl to put in. Well, the moles of KCl, that's my x. When I solve for x, it'll be the moles, but the question wants the grams. So I'm going to solve for the moles and then do a conversion after that. All right, so solve for x, I multiply that over, so x is going to be 0.25 times 2 is going to be 0.5 moles. We're talking about potassium chloride, that's KCl. Okay, so then to go from moles to grams, I know that to go from grams to moles, I always divide by the molecular weight. If I'm going from moles to grams, I have to multiply by the molecular weight. Basically, the conversion just flips over depending on which way I'm going. If you can get that straight in your head, chemistry gets to be a lot easier. So it's going to be 1 mole to the molecular weight. Potassium's 39.1, chlorine's 35.5. So if you add those together, I think that's 74.6. So that's going to be 74.6 grams to 1 mole. If I multiply those, I believe that gives you 37.3 maybe. I may be wrong, but it's 74.6 times 0.5. Okay, that would be the grams of the KCl that I would need to weigh out, put into the 250 milliliter flask, fill it up halfway, shake it, fill it up to the top, got my solution. All right, that's probably a good place to cut off. We'll pick up with dilution on the next